not smooth at all. And I'll ask for it to be simply connected. So now I'll consider some primitive class in the second homology group of this format. Well, primitive here means that it's not a non-zero multiple of some other class. The one thing you might already know is that if you have a second homology class in a four-dimensional manifold, it's always represented by some embedded surface. That's also true for topological four manifolds. And the sorts of things that you may have seen before is that, well, you try to find the minimum genus of such an embedded representative. In Andrash's course later, you'll see lots of sort of smooth obstructions and lower bounds with this sort of thing. But this theorem is going to tell you is that topologically the situation can be very nice. And in particular, whenever you have such a primitive class in H2, this will be represented by a locally flat torus. So in contrast to the smooth setting, where you have sort of lots of these obstructions to getting classes represented by low genus embeddings, in this topological setting, you get a very, very low genus. The original proof of Lee and Moshinsky was relatively abstract. I'm going to give you a more direct, more geometric approach to this theorem. This will be the focus of the two lectures that I'm giving today. The morning will be pretty general and introductory, and in the afternoon we'll actually do that. So this will be extremely, extremely direct and hands-on. Question?
So are you going to talk about the example which cannot be represented by a sphere?
Yes. There is a very specific invariant which I will define extremely geometrically that will describe precisely when this is not represented by a sphere. And there are situations when you can't get a spherical representation. Thank you for the question. Other questions about the statement?
What about non-primitive homology classes?
We'll talk more about that. Short answer is Lee and Moshinsky talk about this, but the proof that I will talk about will be sort of necessarily wanting the primitivity, and you'll see why. Okay. Extremely concrete, explicit, geometric thing. Other questions?
Does the statement change a lot if I1 is not open?
Another thing that we will talk about later. These are all extremely good questions. Keep them coming. I will tell you in a very specific, I'll give you a very precise answer to that later. Let me say for now that there are two results. There's this Lee and Moshinsky result for 97. There's this result of mine with Daniel Kaspersky, Mark Paul, and Peter Teichner from a couple of years ago. They intersect in this statement. They have two different generalizations, and they have two very different restrictions to pi1. By the end of my 4 lectures, I hope you'll know where that comes from, but not right now. But great questions. Other questions?
I'm sorry about that, but so that's an embedded force, right?
Yes.
So if you just allow the immersed one, then you always can represent it by a sphere.
That is step 0 of the proof. You're in a simply connected manifold. So H2 is isomorphic to pi2 by the Hurwitz theorem. So you always get a map of S2 representing. So by the way, in high dimensions, it's always an interesting question to ask, like, is there some manifold for which I have a map representing a given homology class? And so that is a non-trivial question that people have considered. In low dimensions, usually that step is relatively straightforward, especially in the simply connected case. You even get maps from spheres, but they're not necessarily embeddings. 2 + 2 is 4. Makes sense, yeah? And so upgrading a map to an embedding, that's the hard. That's great. Please ask more.
Is closed important?
Those will be important in a way that will become clear. But you can also say that, once again, in the 2 generalizations, they'll be important in different ways. But here I can also say that you could, for this specific proof, you could have the boundary of M be a disjoint union of integer homology spheres. That will also be fine for the proof of F.
Orientable?
No. Don't think
Compact.
so.
Compact.
Don't think so. No.
And can you just add that on and then reduce to close place?
You could, because if you're willing to work in the purely topological setting, which I think you are, then those do bound contractible, compact contractible core manifolds, so you can always snap them off. You might not necessarily know that your spheres that you're building are away from there, so that's something to be careful about. But in general, sure, if you don't mind where if your spheres leak into that region, that's fine. It's great. It's great. Keep going. Anybody else? All right, so extremely direct hands-on proof coming up later today. Hopefully. On the other hand, there are proofs and arguments that are much more indirect, that are much more abstract. These use techniques like surgery theory, things like the H-Cortisone theorem, things that are, not at all direct, things that are a lot more, a lot harder to see what's actually going on. So that will be the focus of lectures 3 and 4. That will be tomorrow and the day after tomorrow. And there, I will talk about these two theorems. I'm going to attribute both of them to Friedman input. So let's say that one was theorem 1. So here's theorem 2. This will be primarily tomorrow. Any one knot with Alexander polynomial 1 is topologically sliced. This one you may have heard of before, especially if you think about knots and slices of knots. Naturally, slice means my knot lives in S3. Slice means there's some locally flat embedded 2-disk inside of my V4. So that's what we'll talk about tomorrow. And then we'll see how the timing goes with all of these things. The last lecture, hopefully, depending on how time goes, I'll prove the following. Suppose now you have a 2-knot of an S2 going into S4, something that was brought up in lecture 1, was you could consider the knot group for this, namely pi1 of the complement of this 2-knot. And we saw in the classical dimension, having that group being infinite cyclic was equivalent to being topologically unknotted. But it was equivalent to being unknotted for classical 1-knots. In fact, that also holds in the topological setting for 2-knots. So depending on how time goes, in lecture 4, I'll talk about the proof of this result. Both of these will use surgery theory. That will be a lot more abstract. So today there'll be lots and lots of pictures. Tomorrow and the day after will be much less. So this is what's coming up. These two for sure, and this one hopefully bigger. So that's what's coming. That's the mini syllabus. Question?
Yeah, I've always thought about like obstructing maybe like the homology class being spherical, but is there exist like homology classes for which like after some K they can't be represented by those?
Do you mean like
Like
after some K, like K would be like genus or
yeah.
something? Yes, whenever you have an embedded genus G representative, you can always add a little
Yeah.
handle to make the genus bigger. So that's why it's always the minimum.
Yeah.
That's interesting because then you can always stabilize. Does that answer your question?
Thinking about how like in C, this might be because it's smooth, but I thought CP2 like the conjecture showed that it was also the lower bound, not the upper bound. And so like wouldn't there be an upper bound for representatives?
So there might be something about like if you are, okay, so the Tom conjecture says that in CP2, the degree D class can be represented by a surface of genus D-1, D-2 divided by 2, not 4, 2, yeah, okay. And that's like a lower bound. And then there's a different result that says that if you have, is it complex surface, then it's genus minimizing. So if you require that your surface is complex, then it couldn't have higher genus than the minimum. Maybe that might be what you're thinking of.
That's exactly.
Sorry?
It has exactly that.
Then it has exactly that genus. But if you're only thinking about smooth or locally flat, then the stabilization process will always increase genus. So maybe the point is like stabilization, of course, will preserve local flatness and smoothness, but it would not preserve complexness and other more rigid structures. I barely know anything about smooth embeddings. I certainly don't know anything about complex embeddings, so you should ask Dave instead. Other questions? These are the theorems that we will prove together. Also wanted to tell you some logistics before we start. The TA for this course is Daniel Hartman. Thank you for doing this. There will be TA sessions, as you all know. I won't really state the problems here, but what I have done is that the problems can be found at that top link over there. I've also attempted to type up some lecture notes, so you'll find the notes from what I thought I would do this morning. The figures are missing. Sorry, I'm working on it. They'll get updated as we progress. If you're working on the problems, you could send me some text solutions and I'll add them to the lecture notes and I'll add your name to it. That would be really cool if you wanted to do that. The homework comes in 3 flavors. Choose your own speed. Some of you are just starting out and have never considered surfaces in 4 manifolds, so don't try to do the hardest problems. But some of you have thought about it a lot. Try to do the hardest problems and help out the ones who haven't done them before. Please ask questions. I think that would be okay. I feel like we're having a good start there. You can also give me some anonymous feedback at that second link. In particular, if this is too slow, too fast, let me know and we can improve for the future lectures. Positive feedback also encouraged. If this is just right, then I probably shouldn't change. And then I set a 5-minute alarm on my phone so that I don't go over time. So if my phone makes a sound, don't be alarmed. My phone is alarmed. This has been the syllabus. How are we doing? Good, reasonable? Okay, thank you. All right, so let's get started. Today we're going to prove theorem 1. And I had intended that we would start off by defining locally flat embeddings, but Mark already did that. Just as a quick reminder, so see Mark's course for the definition of a locally flat embedding. So if I have F from a surface into M, the locally flat embedding, I know that for every point X in sigma, I could look at F of X, and then I could look at a little neighborhood around there, call it U, and I'll know that there's a homeomorphism of this pair U comma U intersected with the image. This is my symbol for homeomorphism, the standard pair R4 comma R2. And if I'm thinking about embeddings with boundary, then there should be some sort of boundary condition. I wrote that in the notes. So I'm going to try to not give you super precise things here, but sometimes the notes will have more precise statements than what I will write on the board. So if you're looking for those, that's where you'll find them. I also want to define something related. So a map from a surface to a 4 manifold is called a generic immersion. If it is locally flat embedding, almost everywhere, except for some isolated double point singularities. So what do I mean by that? I mean, at most points of sigma, if I look over in the image, I'll see a picture like this. But there might be other points of sigma. In this case, my sigma is some torus. I might have some P1 and P2 that will map over into my ambient space so that they both map to the same central point in the middle. My apologies for things being low, can't really help it. So around this sort of double point singularity, I'm still going to get some neighborhood U. I mean, this neighborhood being homeomorphic to that R4, that's just the fact that my ambient space is a topological four manifold. For it to be an isolated double point singularity means that there exists a homeomorphism of U, comma, U intersect at sigma. And now instead of this very nice pair, I'll have this slightly different pair. And still get R4 in the first coordinate. And now I get the XY union ZW plane in the second coordinate, right? So this is exactly what you would expect. This means that locally it looks like the standard pair. This means that add these double point singularities, looks like the standard double point singularity. Okay. So the first thing I want to tell you is that oftentimes people sort of look at the definition of a locally flat embedding and go, how can I possibly work with this explicitly and directly? Because it looks kind of weird. There are these urban legends that these locally flat embeddings are left fractally and like super weird. Can't even draw pictures. How can I be explicit? They're not. They're super nice. And they're super nice in the following way. I want to give you a collection of theorems that are question. So I'm going to start off by giving you some theorems that make it so nice to work with locally flat embedding. The first one is the following. I'm going to call it a theorem, but it's called the immersion lemma, which is weird. This was also first stated in the book of Friedman and Quinn. That says that whenever I have a continuous map of a surface into a four manifold, it's homotopic to a generic immersion. First of all, the moment you have any continuous map of a surface into a four manifold, it's the first thing you might do if you were working smoothly as well. You would say, oh, let's assume it's an immersion and all the intersections are very nice. You can still do that. Okay. So the smooth version of this is the sort of thing you might have seen in a first semester course in differential topology. In contrast, this is extremely hard to prove. This is something you might see in a seventh semester course in topological topology. So it's really hard to prove, but that's fine. Some nice people proved it for us. So we don't have to worry about it. We can just be very grateful that they did. And now we can just use them and our lives are good. We're happy. Here's some other things that these nice people did for us. These are both results of Frank Flynn. Whenever I have a locally flat embedding, in fact, now I will say any locally flat submanifold. of some topological form manifold. Any topological form manifold has a linear normal bundle. What does that mean? Well, here my definition of a locally flat embedding was, well, very local. But this is saying there's something actually very nice and global about it. So in particular, if I'm thinking of a map of a disk, D2 bundles over disks, well, there's only one, D2 is contractible. Right? So this means that whenever you have an embedding, a locally flat embedding of a D2, it extends to an embedding of D2 cross D2. Whenever you have an embedding of some sigma G, it extends to an embedding of some D2 bundle over that sigma G. Again, the sort of thing that you were freely using in the smooth land. And it's very, very hard to prove this, but we have it. Let's use it. This other thing that you might already be using in smooth topology and wish you could use topologically is transversality. So there is topological transversality. So if you have sigma 1 and sigma 2 are locally flat submanifolds of some M4, there exists some ambient isotopy of M taking sigma 1 to some sigma prime such that this result, sigma 1 prime and sigma 2 intersect transversely. So in particular, if you have a one-dimensional thing and a two-dimensional thing, you can assume that they're disjunct. If you have a two-dimensional thing and a different two-dimensional thing, you can assume that the intersections all look like that. Again, the sort of thing you've always been doing in smooth land very happily. You can be just as happy in topological land, and everything will be fine. I am going to say nothing about the proofs of these results. I'm just going to use them gratefully and freely for the rest of these lectures. And I hope that you too will do so in the rest of your life. Question?
Transversality, generic,
What does generic mean to you?
but and also a generic isotopy will carry sigma 1 transverse to sigma 1. Or if that makes sense.
Don't quite know what a generic isotopy should be. Possibly, but I'm not completely sure.
Maybe something like open, yeah, are transversely intersecting submanifolds open and dead.
I want to say possibly, but I'm not sure. If you ask me again, I would like to think about that some more. I have never thought about that before. It seems at least plausible, but let me think. Questions about these statements? Roughly, you should think about, hey, you know those things that I always do to smooth maps and smooth surfaces? I can probably still do them topologically. Okay. All right, so I'm still trying to give you sort of tools. So the next thing I want to do is draw some pictures. So we talked about locally flat embeddings and generic convergence, and they're not as bad as maybe you were worried they were. And I'm going to claim that I can draw nice pictures of them. They're not going to be as nice as Mark's pictures, but they're going to be pretty nice. Well, because by definition, as I just erased, there's always going to be these little neighborhoods in which they look very nice. So in particular, I want to give you a picture of what these transverse double point singularities look like, because we will use them. So how do I think about visualizing these double points? I want to think about this local R4 chart. I don't know how to draw R4, but I do know that R4 is R3 times time. So I can draw you a sequence of R3s, and then I'm going to stitch them together to get all of R4. So maybe I'll have here, it's the middle of, so maybe I'll have here R3 cross 0. Here I'll have R3 cross epsilon. And here I'll have R3 cross minus epsilon. And unfortunately, I deleted it, but remember, for a generic immersion, for a generic double point singularity, I need to think about my XY plane and the ZW planes. So how do these show up in this picture? Well, the XY plane is going to show up right here in the center. I didn't draw coordinate axes for you, but you should imagine they're there. It just makes for a bad picture to look at. So there's an R3 here, and this is the XY plane. And then the ZW plane, in this cross 0 frame of my motion picture, is going to show up as this axis. But in these other sides of time, they're also going to show up as these vertical lines. And it's worth considering, well, if you just look at blue for a second, I hope that blue is visible to everyone. I'm drawing, each thing looks one-dimensional, but I'm going to stitch these one-dimensional things together. The result is something two-dimensional. So I'm going to just stack them on top of each other. The XY plane is drawn much less symmetrically. It shows up entirely in the center and shows up as nothing in the other two. But so these are two ways of drawing surfaces in four manifolds, especially these surfaces. And you can notice that this intersection is at the origin right here. This picture makes sense.
So that blue line is the z-axis or the ZW plane?
The union of all of these blue things together is the ZW plane.
Right.
But just this single line isn't, of course. Does that make sense?
So that's like the x-axis, your time axis. I mean, in the XYW notation, what's the time?
I would have thought that in this epsilon coordinate, this is still the z-axis.
Well, then you would
Do you know what I
have
mean?
XY equals 0.
Time is W,
Time is
that's
W.
right, yeah. Maybe I should have written T. Does that help? T, all of them could have been T. So I'm imagining this three axis
I
in
get it,
each
yeah.
of them, right? And the vertical one.
Yeah.
So that z-axis shifted in the W.
That's it, yes, yes, because, so maybe think about how did I get the XY plane? I had the x-axis, and then I moved it in the y direction, and I got all of the XY plane by doing that. Similarly, in the ZT plane, I could take the central z-axis and then move it in the W equals T, sorry, direction, then I would get that second plane as well. Other questions about this picture? I want to say we will draw lots of schematic pictures. We'll also draw many very precise figures. And this is a very precise figure, modulo my drawing ability, right? But this is a concrete picture. Of course, there'll be a homeomorphism of this to my actual surface. The homeomorphism is where things can get wacky, but it's this. This is what it is. Via some homeomorphism and drawing. I want to use this to give you an example of something we will use later. So that's something, so, just as a, for now, maybe think of it as a proof of principle that we can use these effectively And very concretely, let's consider something called the Clifford torus. What is the Clifford torus? This is a torus that lives in R4. And it's called the Clifford torus for reasons I have no idea. Okay. But what is it? Well, in R4, I have the two R2 plates, the XY and the ZT plates. And each of them has a unit circle. And the Clifford torus will be the product of those two unit circles. So this will be, by definition, the XY unit circle times the ZT unit circle. I'm going to show you how to see that extremely explicitly in that diagram over on the right. So in order to do this, we have to sort of understand this picture a little bit more. First of all, where is the S1 in the XY plane? That one's simple. It's right here. Release that. So that one is this guy. It's much harder to see the S1 in the ZT direction, but we can do it. So what's happening if I think of the unit circle in the ZT plane, here it's going to show up as 2 points, right? Like, here. So over here, there are going to be 2 points. Over here, maybe there's going to be just 1 point. And somewhere should have drawn you some more lines. In between here, also would have had 2 points. And so just like that line was tracing out my ZT plane, I had this 1 point, it split into 2, and then became 1 again. And that's like, I have cut up my circle into this. I don't want to use the word slice, but like slice. No? You see that? And now I have these 2 circles. So the union of all of these orange points is the ZT circle. So now I just have to take their product. But what does that mean? Well, at every orange point, I should have a green circle, basically. So let me just do this over here. It will be a bit nicer. So the Clifford torus will look like this. So there, the Clifford torus. Extremely explicit picture of a surface in a format. I'm very sure Mark was not planning on doing that. So there it is.
Do we want a circle in that XY plane, or is it really just the plane there?
This is just the plane,
Okay.
because it's a bit confusing. Completely agree. But like that was one of the that was like a factor. And I'm taking the product. So there like that one got replaced by these 2. You know what I mean?
Yes.
So at each orange point, I will see the green circle.
Okay, yeah,
That's why
right.
there
Oh, yes.
That's why there are 2 of them, 1 of them. A different way of thinking about this is that these circles, as I move all the way around, these certainly do give you a torus, if you believe that. So it's a circle's worth of circles. And then maybe you want to convince yourself that that in fact is the Clifford torus, and that's, I'm asserting that, but that, maybe think about that. Do you have a question? Same question? Other questions? We will use the Clifford torus in lecture 2, but also super explicit, very friendly torus. All right. Oftentimes, if we're thinking about surfaces intersecting, we will only draw you this middle panel and expect you to sort of fill in these other panels on your own. So oftentimes if you look at papers, you'll just see this. But in your mind, you should now fill in all of these other time coordinates. Another thing you will often see, this is not so much about the Clifford torus. This is just a different way of thinking about embedding immersed double points of surfaces inside of four manifolds, is to do it a lot more symmetrically. So here, like the red surface was like fully in the central panel. That was not very symmetric. And I could have split that up like that too. Now it's no longer the XY plane, but it's like still a surface. I didn't require that an oblique flat embedding has to be the XY plane. To be fair, I did require that a double point does have that go to the XY plane, but I think you'll allow me that. But by now, from my blue surface like this, once again, I can see this transverse double point singularity in the central time slice. But now my surfaces are much more symmetrically distributed around it. This is also allowed, and oftentimes we will also draw this central diagram rather than draw this. So this is another kind of picture you will often see. There's one more thing I want to do in lecture 1, which is to give you the one last sort of big black box that we're not going to peek into, which will be the statement of the disembedding theorem. But before that question?
Do you have names for these syntaxes?
I don't know if Mark has a very technical definition of motion picture, but to me, these are motion pictures, or like movies.
Both of them?
Yeah. So I don't think that, I wouldn't distinguish between them. To me, they are the same. Movie picture sounds weird.
These frames?
Movie frames, maybe. Yeah.
So that'll be for Taurus, yeah.
I have to draw the Clifford torus there. But I like the question.
You're actually kind of having some annulus in the one of the maybe blue maybe, and then you're just having a circle, 2 circles in the middle, and you're actually capping off with another annulus.
I completely believe you, but I can't absorb that at real time. So it sounds extremely convincing. I think you're right. But I think it's a great question, and I'm sure that that's the right answer. I'm not being mean. I can't do that. I'm like, oh no, I have 5 minutes. What will I do?
So in the alternative diagram, are the red lines regarded as 2-dimensional or?
Time to wake up. Sorry.
So red lines are 2-dimensional?
Yes. So this is once again meant to be 2 surfaces intersecting at the origin. And now the red surface is also spread out over time. So all of these reds together build up some F. And all of these G's, all of these blues together build up some G.
So in each time slice, both red and blue have same dimension, or are they?
That's right. Like this is a very explicit picture. That is a line and that is a line.
Okay, so
So red and blue is always a line in each copy of R3. But together, taken together, they form a surface. Before I state the disk-embedding theorem. Hey, I was drawing pictures of R4 and I drew you the X, Y, and ZT planes. But because of my definition of generic immersion and locally flat embedding, these are pictures of every point on your surface, right? And in particular, whenever you have isolated double point singularity, there you will find a Clifford torus waiting to help you. I hope that part is clear. Then now let me state the disembedding theorem. This is a big deal theorem. I'm worried that 5 minutes will not be enough. Let's try our best. So it's a big theorem that could be stated very generally. I want to state it very specifically, just to get us started on the thing we will actually use later today. after I write it, I can tell you more about the generalizations, or you can read about them in the notes. Let me also attribute this to Friedman and Quinn. This will be the prototypical thing that allows us to do anything in topological core manifolds, okay? So its importance cannot be understated. Let me write it in a four-dimensional topological manifold, which is simply connect. This is just for convenience at the moment. More on that later. I'm going to start. I want to embed some disks. So I'm going to start with something like this. Didn't mention the symbol earlier. This means generic immersion. Okay. And then I need not only my disk F needs to have some friend. This will come in the form of a second generic immersion, which will be called G. There will be three properties here. First is that G has trivial normal bundles. Second, G has trivial self-intersection. And that F and G are algebraically dual. Meaning, for trivial self-intersection means G dot G is 0. This means that F dot G is 1. I'm going to draw you a picture. So the picture will look like this. You don't see blue, so pretend this is blue. So this means that I have a picture like this. This is my boundary of M. Here's my F. The boundary of F is embedded in boundary of M. I'm going to quiet down a little bit. I don't need to rush. Darker.
A darker marker, yeah, I can see it.
Darker red. Darker all the colors.
No, yeah, red, sorry.
Time to end. My apologies. I'm going to finish this theorem and that will be the end, I promise. Is that visible? The double line is unintentional. Okay. So I have my four manifold. Its boundary is a three manifold. In that three manifold, I have an embedded circle. It's the boundary of F. That part is embedded. This part is embedded. But then the disk itself might have these double point singularities. And I'm going to draw them always looking like that. That is no longer an actual explicit picture anymore. It just means that locally it would look like this. But okay, this is the best I can do. Then I need to have a friend. My friend was going to be blue. My friend was G. G will look something like this. Yeah, that looks nice. And dark, hopefully that's visible. So G is some sphere. It lives entirely in M. It has trivial normal bundle. I don't know how to draw that. So I won't. Know in your mind that it's a trivial normal bundle. It has trivial self-intersection, which means I'm going to add up these double points. These come with signs. My ambient manifold is oriented. Least orientable. So these come with signs, I add them up. That's what the point two means. So those signs will add up to 0. And then F and G being algebraically dual. That means if I look now at the intersections between F and G, they also have signs. And these also add up to 1. So this is the input of the theorem. That makes sense? Thank you for your patience while I read this. I'm going to move this slightly higher and write it below. Sorry about that. The conclusion of the theorem is that, well, I will embed that disk and I will make that algebraic condition into a geometric condition. So there exists some F bar, which is homotopic to F, rel boundary, and some G bar, which is homotopic to G, no boundary, nothing to worry about, such that F bar is able to be flat embedded. Then G bar, F bar and G bar are geometrically dual, i.e. they intersect at a single point. Now, in poor planning on my part, I'm going to pull down the whiteboard and draw the output. My apologies for covering up the thing that I just wrote. So here's what the output looks like. The output is the following. I'm going to have, once again, the same boundary M. I'm going to try to keep the same boundary. I will fail. This will be my F bar. My G will look like this. I'm certain I'm quite over time, so I will stop for more on this, more history on this. Please see the lecture notes. In lecture 2, we'll just start with the proof of the mean motion speed theorem. Thank you for your patience and questions.
The condition geometric over there.
With the sign, with these intersections.
Yeah.
So what I mean by that is, so it's a bit easier to think about F and G, and it's even easier if F were a sphere. So can you, if you were to imagine that there was no boundary and these were just two S2s in your phone manifold, there's a totally algebraic way of doing this, which is, well, there is an intersection pairing on your manifold. Or you could think about the cup product pairing. These would be classes in H2. They would have concrete duals in H upper 2. Those would have a cup product. You could evaluate that on the fundamental class and get something integer value. That's what's happening here. There is a purely geometric way of doing this, which I prefer, and that's why I'm drawing that. But if you prefer to think more algebraically, all of these things have nice algebraic counterparts. So the geometric version is that I'm in a topological manifold. I'm in a simply connected manifold. Simply connected manifolds are always orientable. Good fact to know. So they're orientable. And then these F's and G's, these are also orientable, because that's a D2 and that's an S2. So in particular, let's just orient them and not care about our choices for the moment. And so these intersections come with signs, which come from sort of taking the orientation on the first guy, second guy, and comparing it with the ambient orientation. And you should convince yourself that if you change all of these choices, all that will change is like the sign of the intersection. So that 0 will become -0. And that might become -1. But plus or minus 1 kind of doesn't matter to us. I could have written plus or minus 1. So that's kind of what I was needing here, that each of these intersections has a sign, and we add them all up. And I want them to be either 0 if I'm thinking about just the G's, or 1 if I'm thinking about the F and G.
Okay, so the not saying the intersection.
Yes, okay, yes. Sorry, maybe I should have just said that, and that would have been okay, but
No, it was right.
and then it's worth noting that, like, here, the homological thing makes sense because there's a 1 row boundary class and 1 absolute class. And there is a nice intersection pairing there. But if you have 2 row boundary classes, super weird because there isn't an actual intersection pairing there. So in that case, the geometric thing makes much more sense in my mind. The algebraic sense becomes a lot trickier, which is weird, but true. But anyway, try not to think about that. Try not to think about what I just said. You don't have to.
I think I'm missing something obvious, but where does this fail smoothly?
I did not tell you where it fails smoothly. The really annoying answer that I can give you is it fails right here, because I just said that the result is open flat. You probably want a better answer. The better answer is that the proof is extremely topological. I could tell you a lot about this proof. I've chosen not to. Roughly speaking, you'll see more about the history of this in the lecture notes. But roughly speaking, what the original thing that Friedman proved was he started off with a smooth manifold. And he started off with these inputs totally smoothly. And then he built something very smooth. But he sort of upgraded this F to some F bar, which was a smooth embedding, but of a thing that he could not identify. And the sort of major breakthrough that he made is he noticed, should have said that embedding was really Cassin's thing. But so Friedman sort of looked at this smooth Cassin thing, and he was only able to show that that thing is homeomorphic to a D2 cross D2.
Okay.
But it's only homeomorphic, and it wasn't a character flaw. It's not diffeomorphic. So it's not that he was unable, it's just not true. But I don't know if that is less annoying an answer, but somehow the proof only shows a homeomorphism, and the smooth version is false. So it's not like open, it's like very nice. Other questions? Am I allowed to do questions? Okay.
I know there's a family version of this there, but
There's a
question.
That sounds like a technical statement. I got worried for a second.
The question is
Family
like,
separate vision?
the question is there a surface version?
I promise I did not ask Itai to ask this question, but the surface version of this theorem is precisely what was proven by Kaspersky, Pavel, Teichner, and myself. Great question. Good job. I doubt I'll have time to state that in lecture 2, but it will be in the lecture notes if you want to. But thank you. There is a PhD. Yep. Complete